Hello and welcome to another video in my lecture series entitled Injection Molding Fundamentals. In the previous video, we had discussed the concept of specifying the right machine for the mold. In this particular video, we are going to acquaint ourselves with the concept of factors which are affecting the design of the mold. So without wasting any time, let's get started. So as you can all see, this is how the agenda is gonna be. We will start with the very basic introduction as to what exactly are the factors which affect the design of the mold. The second thing which is brought to the table is the concept of total equipment productivity, which is the factor which tells us as to how many good parts a mold can produce for a given period of time or throughout his life. Thirdly, we will discuss about the cycle time. Next, estimated annual usage, or we would rather study about projected annual requirements. And then what exactly is the purpose of the mold? What purpose does the mold solve? Is it just an experimental mold? Is it a prototype mold? Is it really a production mold? Right? And there are different examples, right? And then we'll dive deep into the injection molding machine, how exactly it affects the design of the mold, basically the construction and the dimensions or the tie rod distances, those will come into play. Thirdly, we would study about the plant environment, right? What exactly are the requirements from the plant perspective, given the compressed air, so on and so forth. Thirdly, we will discuss about the coolant supply, right? How clean is the water or the coolant water, right? And then we'll study about the power supply, right? So all these topics will be covered in the subsequent videos and will ensure that the whole module, you know, is circumscribed around these videos. So let me take you to the introduction. Okay. So what exactly are the factors, right? So there are different factors which decide as to how the mold has to be designed. Okay. So a specific mold will always operate in a specific environment, right? And that environment can be the machine into which it will fit, and then the services available in plants such as air and cooling, right? And the environment of the plant. So these are the basic factors, right? And these can sound minimalistic, but these certainly have a significant effect on the design of the mold as well as its productivity. And then, even if mold is the heart of the injection molding system, right? And we all know how important a human heart is. So if we can replicate it, or if we can compare it to the mold, if it's the heart, nothing can work if the mold is not designed properly, right? And there are other reasons. For example, if other organs don't function properly, heart also doesn't function properly, which is why a mold cannot operate efficiently if it's not able to function in an environment which is satisfactory, right? And these factors which make the environment satisfactory, all these factors will be going to examine and what impact they can have on the design of the mold. So once we know that these factors are to be taken into consideration, these factors are to be laid down on a checklist for them to be, considered whenever the mold is designed. The designer can accurately specify or estimate how many cavities are required, right? What type of material is required for the mold. Of course, there will be a different material for the mold base and a different material for the inserts. And then what kind of sophistications are required for the mold to have a successful design, right? And that design must work in practicality. So the first thing, the first concept which comes into play, or the first factor which comes into play, is the total equipment productivity. What exactly is? As I told you, it simply means how many good parts a mold can make, right? And I'll give you an example here, right? So if a mold is able to work quickly or mold a high number of parts, that means the cycle time is less. But the mold requires a significant downtime, significant maintenance. There are chances when it can break down, right? The downtime is high, and there are several issues, and it is not able to sustain the production. So that mold is not an ideal mold. The second scenario is, even if the mold makes good quality parts at small frequency, means at a larger cycle time, that mold also is not an optimal mold, because the parts frequency is less and the other consumables are more, which is why the net to net productivity is less. So total equipment productivity tells us how highly productive the mold is, how many good parts it can produce for a long period of time, because it's all about sustainability in an injection mold, because a mold is supposed to last for a long, long time. And basically, there are there is a formula to calculate the total equipment productivity. It starts from the production hours, which is the hours for which the mold is working, right? And then we divide it by available hours, which is more or less 24, because we don't have any more number of hours available in a day. And then what is the scrap percentage? How many parts which are scrapped are produced? And then we multiply it with the cycle efficiency, which is your actual cycle divided by the standard cycle. So we have an example here, right? So we have a 48 cavity closure mold. Closure is your cap, right? There can be a cap which is molded in a 48 cavity mold, right? Cap can be any type of cap, be it a flip top cap or be it a uh, bubble cap, right? So what exactly is required when it comes to calculating the total equipment productivity is something which we are going to understand here, right? So, so the example says that the mold is a 48 cavity mold, and it runs at it is supposed to run at 4 second cycle time, and 10,000 parts is the average scrap which is produced in a day. Average cycling hours is 22.5 out of 24 hours of available time, and there is the expected cycle time of 3.8 seconds. So it asks us to calculate the total equipment productivity, right? So if we write the formula, right? If I am able to write the formula here, right? I'll just go to the sketch mode, right? So what is TEP? Total equipment productivity is your production hours. What is the production hours? So it's 22.5, right? And we divide it by 24, right? And then we multiply it by the parts produced minus scrap parts. So now let's calculate the parts produced. So parts produced will be, I'll just draw a rough line here. So the parts produced will be the in 3.8 seconds, the parts produced are 48 cavities, right? And then in 1 second, it's 48 divided by 3.8, and in 24 hours, that means we have to multiply it by 3600. Is that correct? So we will get the number of parts. Let's calculate it with the help of a calculator. So we have to multiply 48 and 3600 and then divide it by 3.8. This is the actual number of parts, right? So it basically comes out to be 45474, right? Rounding off. These are the parts which are produced, right? So I'll just uh, add 45474, and then how many scrap parts are produced. So per day, this is about 1 hour, right? 1 hour has 3600 seconds. So I'll calculate the the scrap produced in what? 1 hour, right? So if it produces 10,000 scraps in a day, right? So in that case, the total scrap will be your, I mean, I'm calculating in 1 hour, right? So 10,000 divided by 24. That will give us the scrap produced in 1 hour, right? So here, if I go back to the calculator, 10,000 divided by 24. This is 417, right? The answer comes out to be 417. Okay. So I'll just mention here 417 parts. Okay. And then when I divide it by, I need to divide it by the actual parts produced, which is again 45474, beg your pardon. Okay. And thirdly, we have to divide it by the cycle efficiency. So 3.8 is your cycle, actual cycle, and 4 second is your standard cycle. So this whole scenario when calculated, right? Basically 22.5 divided by 24 is your 0.95. Okay. And then we multiply it by the scrap, which is your 0.99. Okay. And thirdly, we multiply it by the efficiency, which is 0.94. So this whole uh, product comes out to be 0.88. So the total equipment productivity is your 0.88 or 88%, right? Total equipment productivity is your 0.88 or 88%. Next, the total equipment productivity, if we have a few things to alter or optimize, right? For example, I'll give an example here. So given 1% increase or 1% change in some factors, let's start with 1% decrease in cycle time. Okay. So let's assume 48 cavity mold, right? Having the weight of the molding or weight of the part as 2.9 grams, right? And then 5.5 seconds is the cycle time, the actual cycle time. Uptime is 90%. We have 3% scrap, right? So if we decrease the cycle time by 1%, that means if we decrease the cycle time from 5.5 to 5.45 seconds, right? I'll just use a pointer. Here, the impact will be an increase, or the impact will be the cost saving of $5,200, which is significant, right? Next, and of course, 2 million more parts can be molded. Like next is your cavitation, which is 48. Now we decrease the weight by 1%. So earlier it was 2.9, now it's going to be 2.87. Everything is going to remain the same. So just decreasing the weight by 1% will give us an yield of 13,000 kg. So 13,000 kg of weight can be saved. Impact or the cost saving will be $8,900. This is value engineering basically. So there is a concept called value analysis or value engineering in production, wherein we optimize certain parameters to reduce the total cost, right? Next, if we decrease the scrap by 1%, right? Everything's gonna remain the same. Scrap, which was 3% earlier, will now be 2%, and the increase, net to net increase in the number of parts will be zero point 0.2 million. Earlier it was 0.2 million with 1% increase in cycle time. Now it's going to be 2.2 million with everything remaining the same, but the scrap being reduced from 3% to 2%. And the impact will be your $5,900, which is again very significant. Lastly, 1% increase in uptime. If it was 90%, now it's 91%, and everything's going to remain the same. The impact will be 3 days. Just imagine the there will be a saving of 3 days, right? And again, the cost saving will be 6,300. By 3 days, we mean the uptime or the time for which the mold will remain active or will continue to produce parts will be increased by 3 days. So this is how 1% change in certain important parameters can impact when it comes to cost saving. Well, this was something which I intended to convey. There can be shortcomings during the delivery of the video in terms of quality of the content or in terms of how it was presented, for which I apologize from the bottom of my heart. But I have really tried my level best to make sure that the knowledge transfer has been made. And I really appreciate you guys watching this video. I'll see you in the other video, and thank you for watching this video.